right. Hello, everyone. And we're just going to wait another minute or so before we kick things off. Just waiting for some more people to come on and have the YouTube channel go live. All right, so I think we should begin. We don't want to delay too long. And so thank you everyone for attending another of our UniKORN seminars. So today I'll be chairing today's seminar, and we're very happy to have Alessio Belanchia, currently from Stuttgart, but is a Marie Curie research fellow at Queen's University Belfast. So just some preliminary stuff that I want to go over. There's a quick announcement for some interdisciplinary research hiring that's going on in an interdisciplinary research institute. And the job post is up right now, and you can have a look at that. And a quick reminder of the simple house rules. For those who are joining us for the first time, welcome, and just be, as always, of course, be respectful for everyone that's there. Can I request everyone that's on Zoom to mute your mics and make sure your videos are closed during when this talk starts. During this question and answer session, if you have questions, you can type them, whether you're on the YouTube live chat, you can just type Q and then type your question. If you're on Zoom, you can also ask your question directly by simply raising your hand. So there's a raise your hand symbol in Zoom. If you utilize that, then I will allow you to open your mic and ask the question directly. That said, I want to quickly just, sorry, one sec. I'm currently monitoring YouTube at the same time, so there might be some times where I'm lagging behind. I just also want to give a quick biography introduction to Alessio. So he obtained his PhD in 2016, I believe, from CISA, working on quantum gravity and optomechanical setups. He then did a postdoc at Lens in Florence, collaborating with Professor Marin. And then after that, 2 years he spent in Professor Bruckner's group in Vienna, also working with Professor Aspermeyer, I believe. And then in 2018, he got the Marie Curie and currently is still in Queen's Belfast. So he'll be talking about his work, and very excited to that. So I'm going to stop sharing my screen, and Alessio, if you take over.
Yeah. Okay, I guess that you can see my screen right now. Let me just move. Okay, perfect. So you should see my screen right now. I can close this stuff here so it doesn't stay in the middle. Okay, good. So I will start right now. Thank you very much. Well, first of all, I would like to start by thanking the organizers of the UniKORN seminars. both for the organization and also to inviting me here today to speak. It's very nice. And today I will speak about one of our last works from the Quantum Technology at Queen's Group, and in collaboration with the Niels Bohr Institute in Copenhagen, and in particular with Professor Albert Lisser group. And this work is about the experimental assessment of entropy production in a continuously measured mechanical resonators. Now, before properly starting, let me just acknowledge the people that made this work possible. And in particular, I start from the top left with Massimiliano Rossi, that is the first author, and then going anti-clockwise, we have Luca Mancino, Gabriel Landi, Mauro Paternostro, and Albert Lisser. And here in the center, there is the reference to the paper on the archive. I put here also another reference to a previous paper, which is the theoretical paper. And since in the title here there is experimental assessment, let me just make a small disclaimer. I'm a theoretical physicist, so when I will speak about the experimental setup, I will do it from the very idealized point of view of a theoretician. But to give due credit, the people that actually did the experiment are the two here on the top, Massimiliano and Albert in Copenhagen, and the other three, and including myself, we did the theoretical part. So in a certain sense, we did the easy job. And finally, just a tiny bit of shameless advertisement. Our paper that I will talk about today has recently been accepted in Physical Review Letter as an editor suggestion. So check it out, because soon it will be out, even if the version that has been accepted will be more or less the same as the one that you can find on the archive. So having said that, let me just explain a little bit what will be the plan of this talk. I will start by introducing a little bit and motivating a little bit the problem of how to define entropy production for continuously monitored quantum systems. And in doing this, I will use optomechanical setup as a sort of paradigmatic example to show some of the shortcomings of definition of entropy production that are present in the literature. And then I will introduce a PhaseSpace method, or at least skim briefly through it, a PhaseSpace method that allow us to identify entropy production and allowed us to observe entropy production trajectory by trajectory in the experiment that Massimiliano and Albert did in Copenhagen. So let me start with standard thermodynamics that you all probably know and love. And let me consider a system, a very simple situation, a system that is an egg that is falling down from my kitchen table and breaking down on the floor, which is, by the way, also one good reason why I shouldn't be allowed to be in a physical laboratory and why I'm a theoretical physicist. So in this case, the second law of thermodynamics tells us that, well, first of all, I have a system that is the egg in interaction with the thermal bath, which is the air in my room at temperature T. And the second law of thermodynamics tells us that the variation of entropy in this process is always greater or equal than Q over T, where Q is the heat that is exchanged between the system and the environment. Now, you can always rewrite this inequality as an equality by introducing here the irreversible entropy production. And then the second law of thermodynamics is encoded in the fact that the reversible entropy production is always greater or equal than zero, equality holding when the process is reversible. And this quantity, or in particular its rate, which is what I will focus today on, are fundamental quantities in non-equilibrium thermodynamics. They encode the second law of thermodynamics. In this case, the rate has to be greater or equal than zero. They essentially quantify the reversibility of thermodynamical processes, but they also enter, for example, in bound on the efficiency of thermal machines and in the response of the system to thermodynamical forces. So they are really the central object in non-equilibrium thermodynamics. And here, it arises the question that we try to tackle in our work, well, at least in the theoretical work, and then we try to look up in an experiment, that is, how do we define the entropy production, irreversible entropy production rate in quantum systems that are continuously monitored. Now, as you can imagine, this question has many answers. Actually, there is no a unique framework for the definition of the entropy production rate in quantum systems. And here I would like to use an optomechanical setup that I sketch here in this figure to try to highlight a couple of shortcomings of the standard way of defining the entropy production for quantum system. And in this sketch, in this figure, I have the prototypical optomechanical setup in which I have, for example, a mechanical mode that can be a levitating nanoparticle interacting with the cavity mode. And then there is also a measurement of the output mode of the cavity through, for example, an homodyne detection scheme. Now, the first way in which you define usually the entropy production rate, also for open quantum system, is essentially using the same way as you do for classical system. So one has to define an entropy rate, and usually the entropy measure here is the von Neumann entropy. And then it has to subtract to this quantity, capital phi, the entropy fluxes, which are usually identified with heat fluxes to a thermal environment. And here, there are at least two shortcomings that are evident if we look at the optomechanical system. The first one is that part of the environment of our optomechanical system is the output mode from the cavity. But for optical frequencies and the standard condition for the experiment, the thermal occupation number of the output field is essentially 0. The output field is equivalent, in the end, to a thermal bath at almost 0 temperature. But in that case, the quantity that we identify phi with, that is Q over T, or the rate of Q over T, is clearly not well defined, because for T goes to 0, that quantity diverges. And indeed, if you consider the structure of the entropy production rate, you can find that in the case of a system in contact with the thermal bath and using the von Neumann entropy, this rate can be written as the relative entropy between the state of the system and a target thermal state at the temperature of the environment. But when the temperature is 0, the target state is a pure state, and we know that the relative entropy with respect to a pure state is a divergent quantity. So essentially, we are in a situation in which these two quantities are actually unphysical, are divergent, while, of course, their sum is still something completely meaningful. And this is still a case in which we have a thermal bath. But looking again at the picture of the optomechanical system, we see here that there is not only the output mode here as an environment, there is also the detector, and there are also other sources of the coherence, for example, the phononic environment here, the optical of the mechanical mode, and other sources of the coherence, which in principle, or at least in general, are not in thermal state, are not thermal reservoir. And in this case, we don't even know how to define Q over T. That is not well defined. We really don't know how to define it. So this first very common way of identifying the entropy rate by defining phi and identifying phi with the entropy, with the heat fluxes it cannot be used in general. There are other ways, of course, in the literature to go around this problem. One of the most general is to define the entropy production in terms of correlation between the system and the environment, and the correlation in the environment itself. However, while this can be applied to the case that we are depicting here in this figure, it is kind of useless for all practical purposes, in the sense that here the environment comprises the detector, which we don't want to include in the microscopic description, and also other part of the environment that are the other channel of the coherence channel we don't have control over. So essentially, we don't have access to the correlation in the environment, and this second way of defining entropy production is not useful for every practical purposes. And here it comes into the game this work of 2017 of Santos and Gabriel and Mauro, in which they introduce a phase-space method to define in a unique way, and just from the dynamics of the system, the entropy production rate and entropy production and entropy flux rate. Now, in this paper, they consider a Gaussian quantum system, which is exactly what I will do in the following. But just as a disclaimer, these formalisms can be extended beyond Gaussian state and Gaussian measurements. So in this phase-space method, the starting point is the use of the Wigner entropy instead of the von Neumann entropy. The Wigner entropy is just the Shannon entropy of the Wigner function in phase space, that for Gaussian system is a Gaussian, so everything is well defined. And this entropy and the entropy production rate and fluxes that one can derive from the phase space approach have very nice properties. First of all, this entropy is for Gaussian states essentially correspond with the Rényi-2 entropy, and we already know the Rényi entropy are thermodynamically significant, but more specifically, the rates that one can obtain from this entropy, so entropy, flux, and production rate, show no divergence even if the system is in contact with the thermal bath at 0 temperature. The formalism can be applied for any non-equilibrium state of the environment as far as Gaussianity is preserved, and the Wigner entropy converges to the von Neumann entropy in a sensible classical limit, that is the limit of high temperature. In this sense, also the entropy production rate and fluxes converges to the classical result in this limit. So this gives you kind of coherent thermodynamical framework, and this framework was developed for open quantum system that satisfy a Lindblad-like master equation. And without entering into the detail of this that you can find in this work, the entropy production rate can be identified in this phase-space method as the quadratic form in the probability current in phase space. So it's possible to uniquely identify the entropy production rate. Now, what we did in our theoretical work and what we looked at in the experimental work that I cited at the very beginning of this talk was to extend this formalism to the case in which, apart from the open system dynamics, we are also measuring, continuously monitoring the system with weak measurements. And in order to describe what changes in the thermodynamics of the system due to this continuous monitoring of the system, and to connect this to the experimental work, I will just use as an example the experiment that Massimiliano and Albert did in Copenhagen. So let me just spend a couple of words on this experiment. It's an optomechanical experiment in which the mechanical mode is essentially a membrane. Well, is a vibrational mode of this central defect in this photonic crystal, and this is inserted in a Fabry-Perot cavity. This is probed with the laser as usual, and then there is an homodyne detection that gives you an homodyne current as result. And further detail about this model are discussed in this physical review letter of Massimiliano and collaborators of last year. And in this case, the system is described by the following stochastic master equation. Now we'll try to see if this works. Yes, it seems that this works. So the system is described by this stochastic master equation, and in particular, this is an equation only for the state of the mechanical resonator. This arises from the fact that in the dynamical regime in which the experiment is performed, we can adiabatically eliminate the optical mode, and we remain just with the mechanical mode. So here in this equation, you see that there is a first part of the equation that is not stochastic, and is the usual Lindblad master equation for an open quantum system. However, there is also a second term here which is stochastic, and the stochasticity is encoded in the presence of these independent linear increments that are random variable. And this stochastic term serves to describe the effect of continuously monitoring the system. So the state of the system is conditioned on the particular outcome that we are registering in our homodyne detection scheme. Now, the other important stuff that are present in this formula are essentially just eta, that is the efficiency of the detector. So you see that if eta is equal to 0, we go back to just having the so-called unconditional dynamics, so the dynamics described by just open system dynamics. And the other important element of this equation are the two Lindblad superoperators that, for the sake of completeness, I report here. There is a first Lindblad operator that is describing the interaction of the mechanical mode with a phononic thermal bath, that is the usual optical master equation. And then there is another Lindbladian that describes the so-called quantum back action. This comes about from the adiabatic elimination of the optical mode, and as you can see from the shape, is not interaction with a thermal environment. Now, this is very nice. This is a stochastic master equation, but is a tall order to resolve this equation in general. However, for optomechanical system in the linear regime and in general dyne measurement, among which homodyne measurement, given an initial Gaussian state, this stochastic master equation preserves its Gaussianity, which means that we can we can exchange this stochastic master equation for a set of stochastic differential equations that are way easier to solve. And these are the equations just for the first and second moments of the Wigner distribution, which is enough to describe the full evolution of the system given the Gaussianity of the state. Now, here there are a couple of interesting facts to observe. The first is that the first equation is actually a stochastic differential equation. This is equation for the first moment, and the stochasticity is encoded in the presence of this Wiener increment. However, this Wiener increment can be solved using this relation between the trajectory in phase space, the Wiener increment, and the homodyne current. So using this relation, we can get an equation for the trajectory that is determined by the stochastic outcome coming from the homodyne detection. So essentially, we can relate immediately the stochastic trajectory in phase space of the first momenta with the experimental results. The second equation, however, is a deterministic equation, and this is the equation for the covariance matrix, or in this case, just the variance of the quadrature of the system, which, by the way, are represented by x and y. Sorry, I didn't say this before, but x and y here are the position and momentum quadrature of the mechanical oscillator, the dimensionless one. So the second equation is deterministic, which tells you that the evolution of the variance is independent of the particular outcome of the measurement, but this make also the determination of this variance from the experimental data a bit more tricky than for what regard the trajectories. Now, before coming to this, let me just describe what happens when we start this experiment. So here I have a picture of phase space for this mechanical oscillator, and this circle here represents the initial state of the experiment. Now, in the case of the experiment that Massimiliano and Albert did, the initial state of the mechanical resonator is the steady state of the unconditional dynamics, meaning that the initial state is obtained by essentially putting to zero the efficiency of the detector, not detecting, essentially, and waiting for a sufficient time. After a certain time, the state will relax to its steady state, which still is a thermal state, but is a non-equilibrium steady state for the system. So the system will relax to this state, and then after this, we start to detect, to do the measurement. And when the measurement starts, the evolution of the state starts to be a random evolution in phase space. So this red curve represents the random evolution, the random trajectory of the mean quadrature of the system, and the variance starts to shrink. As you can see, the dynamics of this system is such that if we start from a circle, we get still a circle at each subsequent time, meaning that we don't have actually a covariance matrix, or the covariance matrix for the system is trivial, is the diagonal matrix and is proportional to the density. This is why here I have just a scalar equation. By the way, what is happening during this evolution is that the variance shrinks, meaning that there is a cooling of this system. And if we repeat this experiment many, many times, this is what we will get, let's say, at the final time of this trajectory by repeating the experiment. So as you can see, you obtain always the same circle because the evolution of the variance is deterministic, but the position of the circle in phase space is random. The nice thing here is that if you average over all possible trajectory, what you get back in the end is essentially the bigger circle that was the initial state. And this essentially tells you that the average over all possible realization, over all possible trajectory of the conditional state is the unconditional one. And remember that we started from an unconditional state that was also the steady state of the dynamics. And so, of course, this remains the same all over whenever we don't measure the system or whenever we average over all possible realizations. Okay, having said that, and before going to the thermodynamics, finally, the last piece of information that I have to give you is how do we connect the variance? How do we get this variance from experimental data, so from our homodyne current? Well, unless you want to do a tomography at each time of the state, the only other way that I know to get this variance from directly from the homodyne current is using what is called retrodiction techniques or the past quantum states. You can find details about this in this Physical Review Letter 2013 or even in the paper of Massimiliano last year. But in a nutshell, what this retrodiction technique implies is that given a record, given an homodyne current, we can split the record in two essentially. With half of the record, so until time, let's say t0, we obtain a predicted trajectory for the quadrature of our system. And with the other half of the record, we retrodict a trajectory technically for an effect that is an element of a POVM, but this is just a technicality. We can just retrodict a trajectory for a certain state or for a certain quantum operator. Now, these two trajectories are given directly from the experimental data, so we can take a relative trajectory, that is the difference between the predicted and retrodicted trajectory, and compute experimentally from the experimental data the variance of this relative trajectory. It is then now not easy but straightforward to show that this experimental quantity is directly connected with this guy here, with the variance of our quantum state. So essentially, in this way, we can also get access experimentally to the variance of our Gaussian quantum state. And now, the last two slides about the thermodynamics. So now I have explained to you more or less how the experiment goes, again, from the theoretical point of view, and what are the relevant quantities. And at this point, one can apply a generalization of the PhaseSpace method introduced in 2017 to the case of continuously monitored systems, so essentially to the case of a stochastic master equation. Again, by just using PhaseSpace method, of which I will not go into the detail because I don't have time, it is possible also for monitored system to uniquely identify the entropy production rate as the quadratic part of the entropy rate, quadratic in the probability current in phase space. However, contrary to the previous case of the unconditional dynamics, in this case, the entropy production rate and entropy flux rate are stochastic quantities. So we can observe them, and we did it experimentally, for every trajectory of the system. And the result is something like this. In this figure, you can see in light blue the entropy production rate and entropy flux rate for a sample of trajectories of the system of the mechanical resonator. And then we can also compute the average over all the trajectory of these stochastic quantities. Now, here is a tricky part, which is that the average of the entropy flux over all trajectory, this capital phi, actually coincide with the unconditional one. So if you were to have a system in contact with the thermal bath, it would coincide with the heat flux to the environment. However, the same is not true for the entropy production, as you may have expected from the fact that the entropy in general is not linear in the state of the system. In this case, it is possible to show that the entropy production rate can be written as the entropy production rate of the unconditional dynamics, so the entropy that is produced just due to the open system dynamics, plus something that I will call an informational term. And I will justify it in the next slide why I'm calling informational. Just for the moment, believe me, it's just connected to the information that you acquire during the measurement. And what is more, we can also use the second law of thermodynamics here for the open system dynamics. We know that this quantity has to be greater or equal than 0, and we can use this to formulate something like a refined version of the second law for continuously measured Gaussian systems. Now, this I dot in the experiment is always negative. However, it's easy to find a physical example in which this is not the case. And note that whenever this I dot is greater than 0, this form of the second law is stricter than the usual one in which on the right-hand side you have 0. Okay, now the last point that I have to make in the last 2 minutes that I have is why I'm calling this I dot an informational term, apart from the fact that here, of course, I have the unconditional dynamics, and then the rest has to be connected somehow to the fact that now I'm also measuring the system. Now, the justification for calling these I dot and informational terms comes from the fact that you can show that I dot is the rate of minus a mutual information, where the mutual information is the mutual information between essentially a random variable representing the unmonitored dynamics of the system in phase space and the random variable representing the output results of our measurement. So essentially, minus I tells us how much information we can get by measuring the system with respect to the case in which we don't monitor. And from the experimental data, we were able also to reconstruct this I dot because we have the exact form. And this is what the data look like. So here, what you can see is that asymptotically, this I dot vanishes. And this is physically meaningful because it's telling you that asymptotically, the state of the system will reach the steady state of the conditional evolution. And at the steady state, you are essentially not acquiring any more information than what you already acquired in the past history of recording. However, from the explicit form of I dot, you can see that there are two competing terms here. A first term is a kind of a noise introduced by the phonon buff. If there was only this term, you will have a loss of information and you will essentially go back to the unconditional steady state. So your state in our case the system would warm up again and go back to the unconditional steady state. However, there is also a second term here. Now, the second term is with minus, but remember that I dot is the rate of minus the mutual information. So this second term is an information gain. It's proportional to the efficiency of the detector, and physically tells you how much information you need to get from repeated measurement in order to keep the system in the steady state of the conditional evolution. So from this point of view, the steady state of the conditional evolution is an informational steady state. It requires a constant inflow of information that we can estimate from this term in our informational quantity. So with this, I have actually concluded. Let me leave you with, it works, yeah. Well, here there was a thank you slide, but let me, no, it's going out by its own, sorry. I go back. Let me leave you with a summary slide. So what I have shown you is that we have a phase-space formalism that can account for the thermodynamics of mesoscopic mechanical resonators that are continuously measured. And we were able for the first time to observe the entropy production rate and entropy flux rate for a continuously monitored mesoscopic mechanical resonator experimentally. And finally, the second law of thermodynamics for this kind of system shows that the information, the act of measuring the system, of course, have important implication on its thermodynamics, as it is also well known from the field of information thermodynamics. So with this, I have really concluded. Sorry for being a bit over my time, and thank you very much for the attention.
Thank you, Alessio, for that very interesting talk. I think we can, so the general way we do this is if we can unmute and just clap to acknowledge and thank you, Alessio. Everyone can unmute them. Thank you for that. So if there's any questions, please do ask away. I'm just going to have a quick check on the YouTube if there's any. Okay, I think while people are still digesting the talk, so I had a few quick questions. This is really, Alessio, my ignorance that will show. So when you talk about conditional and unconditional variance, what does that mean exactly?
Yeah, so, yeah, sorry, I was fast there. So the unconditional one, let me take the master equation. So the unconditional dynamics is the one given by just the open system dynamics, so the standard Lindblad equation. The conditional dynamics is instead the evolution of the state conditioned on the outcomes of the measurement. Okay. Now, for what regard the variance, this implies that the unconditional variance of the state is this big circle in our case. And as I said, we take an initial state that is the steady state of the unconditional evolution. So if there was no measurement, the state would remain this big circle for every time. The conditional variance instead is the one that comes from solving this equation. So the one that appears whenever you start to measure the system. And if you start to measure the system, as I said, in this case, this variance will shrink down. Another way to see this is if you send to zero here the detection efficiency, you remain with an equation that that is an equation for the unconditional variance of the system. So essentially, the difference is in which equation you are solving, and the difference is on the fact that in one case you are averaging, if you want, over all possible measurement, while in the conditional case, you are conditioning the evolution of your system on the result of the measurement, so that you have, every time that you run the experiment, you will have a different trajectory.
Okay, thank you for that. I think, Sugata, you have a question, please.
Hi, Alessio. Hi. Very interesting talk. Yeah, I have a couple of questions. So firstly, what is the method, is a general method of calculating this entropy production? So suppose I wanted it to apply to some other system, say a spin chain or something like that, and wanted to see this entropy production.
Yeah, so for what regard the formalism, the explicit expressions that we have are for Gaussian systems. So of course you can apply them to any Gaussian system. For what regard, for example, spin chain, then you should go beyond the Gaussian framework, which is what I was pointing towards before. There is Mauro and Gabriel have a paper in which they use the Ver entropy, that is the entropy of the Usemin function. And in that case, you can use the Usemin function also for spin system without any problem. So in principle, yes, and our formulas can be adapted also beyond the Gaussian case for continuously measured systems.
Okay, that's very good. That's nice. And is there any calculation of like repeated von Neumann measurements rather than this continuous one for?
In the literature, I think there is something. For sure, there are the papers of Sagawa and Ueda in which they consider discrete measurements and, well, usually something like one measurements and stuff like this. For continuous measurement, I don't know. I mean, continuous measurement in the end are weak measurements. So I would say that it's a different story. But yeah, there are works in which they consider also projective measurements.
Okay. Thank you very much. Yeah,
welcome.
It was very enjoyable.
Okay. Are there any further questions from anyone? I still have another question. Sorry, Alessio. I'm hogging this space. So just actually going to this diagram, just to clarify for myself. So experimentally, what you're doing is of course you've got some oscillator and you shine a laser and you're just picking up the motion of that in the light. Yeah. And that gives you the current
yes.
IT.
Yes. You monitor the output field of cavity.
And so what you're saying is that is a continuous measurement at say time intervals of short time intervals, but for every time it's measuring, the smaller circles are being created. Is that what you're saying?
Yeah. You are measuring. Yeah, this is a continuous trajectory. So you are continuously measuring the system. The system is undergoing a stochastic trajectory in phase space because the trajectory depends on the outcomes. So here, essentially, I don't have a plot, but here, essentially, you will have a sort of stochastic plot of the current coming from the Modine detector, and that reflects in a stochastic trajectory here. But the circles are always shrinking in the same fashion because the equation is deterministic. So you are cooling down the system, but you end up in a random point of the phase space at every round of the experiment. But
that's simply by measuring that you're cooling the system down.
Essentially, you have your system, and then you're measuring the output field. And when you measure the output field, you are essentially reducing the state of the system. Of course, it's not a projective measurement, so you're not reducing it to a pure state. You are just reducing it in a weak way, but in any case, it's enough to cool down the system. And in principle, you could even make the state pure in this way, so you can really cool down to the ground. The only difference between this system and what is done in feedback cooling is that in feedback cooling you have also feedback mechanism that are such that instead of ending with this kind of plot, every time that you arrive at a certain point, you take the system back to the origin. So in the end, if you have feedback control, you will have something similar to this, but all this circle will be here at the center of the phase space. So you know even where you are and you go towards the ground state.
I see. Okay. All right. Okay, that makes sense. Thank you. Oh, there's another question from Ignacio. Please.
Thank you very much for the nice talk. So it's also a bit ignorance. I think I'm a bit confused with the actual measurement. I'm more used to this homodine where you just get one quadrature out, and then from this thing, but you have the two at the same time. So there are two linear increments. Yeah. Could you explain a bit how that works and to what basically setup this corresponds in terms of the measurement?
Yeah, this actually is, thank you for the question, because this comes from the fact that this equation, this master equation here is an effective master equation. As I said at the beginning, the full system would have something like 4 quadrature because you have 2 quadrature for the mechanical resonator, 2 quadrature for the optical mode. However, this equation comes from an adiabatic elimination of the optical mode, and in this way, you can, by doing the derivation, you can see that actually the homodine current gives you information of both the quadrature of the system. Again, is information about the average value of both the quadrature. So you're not violating anything like Heisenberg inequalities. But yeah, this form with the two binary increment comes from an equation in which there is just one binary increment at the start to start with, but then the adiabatic elimination and other approximation lead you to this equation here, so that in the end, by doing essentially something like a filtering of the outcome of the detector, you can trace both quadrature of the mechanical resonator.
So there is like some kind of time bins that you use concerning your photocurrent.
Yeah.
I mean, I have the photocurrent. If you just average this random thing, you get. You
are essentially filtering the result. This is
so there is like some filtering involved in this digitizer story.
Yes, there is a filter.
Okay.
Yeah.
Okay, thank you very much.
You're welcome.
Okay, great. Since there aren't any further questions, Alessio, once again, thank you so much. And thank you for everyone else for joining in. So just to remind everyone that we will have our next talk next week by Dr. Laure Le Penay at 2 p.m. And hopefully see everyone there. Thank you.
Thank you.
Bye.
Bye, everyone. Thank you.
Bye.
Bye, Alessio. Bye, everyone.
Bye-bye.